Hello all, welcome back to the next video on material science and metallurgy. Myself, Dr. A. Varun, and we were discussing a very important topic, that is iron and iron carbide phase diagram. So let us quickly revise once again and then go back to what we were about to focus, that is on the steel part of the iron carbide diagram. But before that, like I said, let us understand. So we had our discussion wherein I said we can be remembering this iron carbide phase diagram as easily as we need to segregate into three zones. And always remember, there is a representation of pure iron and followed by the carbon when it is alloyed. So if you recall, I said that these temperature 1539 marks the freezing temperature above which there is a liquid, and below that there will be delta iron. And then 1400 below you have what is called as gamma iron, and 910 below you have alpha iron. And why are we not representing 768? Because 768 is only transition from non-magnetic to magnetic, so that is ruled out. Then comes, there are three horizontal lines, one horizontal line here at 1492, another one here at 1147, and the third one is 723 here. And remember, this line, what you see is a dotted line, is construction line, not part of the iron carbide phase diagram. Similarly, there is this small dotted line, what you can see here and here. Okay. Now, remaining all is part of the iron carbide phase diagram. Okay. So I just want you to understand that this is not part of the iron carbide phase diagram. It is only for representation, to show you that I am trying to mark this line. Okay. So this line here, which is 1147. Anyway, so let us mark in the other zones. So it's very easy. Now this side delta, and here it is liquid. So you have here liquid plus delta, and delta here, gamma here. So in between delta plus gamma, delta here, liquid here, gamma plus liquid, and alpha here, gamma here. Yeah, liquid plus Fe₃C, gamma plus alpha. So the remaining things are about the percentage of carbon. So delta maximum 0.1, and the reaction takes place at 0.18. Maximum it can go to 0.5. And this reaction Eutectic takes place at 4.3, and maximum gamma is up to 2%. And gamma iron, the Eutectoid reaction occurs at 0.8, and alpha maximum is 0.025, and at room temperature you have 0.008. Then, like I was saying, there are horizontal lines which mark the indication that there is a reaction, or the invariant reaction we call, occurring at 1492, 1147, and 723 degrees centigrade. So what are these reactions? So first reaction is peritectic reaction at 0.18 percentage of carbon and 1492. This liquid plus delta iron will give rise to what is called as gamma iron, and this gamma iron is given a name called austenite. Then the second reaction is occurring here at 4.3 percentage of carbon, wherein 1147 degrees centigrade, 4.3 degrees percentage of carbon gives rise to ends of the line, which is gamma on one side, Fe₃C on the other side. So liquid gives rise to gamma iron plus Fe3. Gamma is called austenite, Fe3 is called cementite, and this mixture of austenite plus cementite is called lead burate. Then we have the third reaction here at 723 degrees centigrade and 0.8 percentage of carbon, which is a Eutectoid reaction. And this gives rise, like austenite is giving rise to alpha iron, which is ferrite, and other end it is cementite. And this mixture, by the way, is called as perlite. Anyway, so 0 to 2% of carbon is called steel, and 2 to 6.61 is called cast iron. And we have Eutectoid reaction at 0.8. Less than Eutectoid is called hypo. More than Eutectoid is called hyper. So you have hypo Eutectoid steel, hyper Eutectoid steel, and hypo Eutectic cast iron, hyper Eutectic cast iron. Now let us focus on the steel part. So steel is from 0 to 2% of carbon, already we discussed, and we only focus up to the austenite zone, because higher temperatures there is no stability, and it obviously gives us a change in the structure. So we will consider from 2 to sorry, 0 to 2% of carbon, and maybe close to 19 degrees centigrade only. Now, if you observe closely, we have this line, which is represented by A3, and there is another line ACM, and at the bottom you have A1, A3, comma 1. If we give a name to it, A3 is represented as upper critical temperature line on the hypo-eutectoid side of the steel, because you can see this is upper line and this is on the hypo, less than 0.8 hypo-eutectoid side of the steel. And this A1, obviously you might have guessed, lower critical temperature line on the hypo-eutectoid side of the steel. Similarly, ACM, this also is very easy. You might have guessed ACM is upper critical temperature line on the hyper, which is because it is more than zero point 0.8, so it is hyper-eutectoid side of the steel. A3, comma 1 will be lower critical temperature line on the hyper-eutectoid side of the steel. Now, these lines mark certain changes of transformation. So we are going to see, but let us take in stepwise. That means let us consider a 0.4 percentage of carbon. That is how this alloy will transform from 0.4 percentage of carbon to room temperature. So let us take zero point 0.4. So at 0.4, if you take any point here in this zone, this is where you have austenite, right? Like this, maybe the grain structure will look austenite. What will be the carbon composition of this austenite? So first of all, how many phases are present? Yes, one phase, which is austenite, single phase throughout. What will be the carbon percentage? If you recall in the liver rule, I said per single phase, straight away you can take the composition by reading it on the x-axis. So it is zero point 0.4. So this is where at any given austenite position, you have carbon, which is 0.4 percentage uniformly distributed in this zone. And this happens to be so until it reaches this line, which we called as upper critical temperature line on the hypoeutectoid side of the steel. What does this indicate? This line actually indicates allotropic change. Yes, at 910. So you can see this is where allotropic change has to start from gamma to alpha. So since we have added carbon, it has dropped, and this line indicates allotropic change. So this line is a beginning of allotropic change. What type of change? From gamma to alpha. So gamma, if you remember, it is in the FCC crystal structure. Now, when FCC crystal structure has to change to BCC, which is alpha iron, it cannot happen when carbon is already present. So what it will first do, it will first remove the carbon which is present, and then it will change from FCC to BCC, and then it will form that BCC crystal structure. Okay, so when the carbon is coming out, so you can see here there is some portion of carbon which is coming out. That carbon needs starts to form alpha, which is nothing but that's ferrite. So in order to form ferrite, it needs only 0.025% of carbon. So if you see in this particular case, 0.4% of carbon is coming out, and it only takes 0.025% of carbon to form this ferrite, which is shown as yellow portion here. And what about the remaining carbon? That remaining carbon will be absorbed by all the neighboring austenite. So this continues to do so until it reaches austenite. All the austenite will attain 0.8 percentage of configuration. That means all the carbon which is present inside the austenite will come out and form ferrite at different zones, and formation of ferrite is required only 0.025 percentage, and the remaining carbon will be absorbed by the neighboring austenites in order to get 0.8 percentage of carbon. Why specifically 0.8? Because it wants to take part in the Eutectoid reaction. And remember, no austenite is stable below 723 degrees centigrade. So this line is a deadline. So below this, austenite is not stable, it's not available. Austenite has to take part in the Eutectoid reaction, because that line indicates the end of Eutectoid reaction. So austenite will change into ends of the line, which is ferrite plus cementite. So what will happen below that? Once the austenite is attaining 0.8% of configuration, then that austenite will change into alternate layers of ferrite and cementite mixture, which is called perlite. If you remember, we have discussed this perlite reaction, right? So we get perlite. So let us quickly see that perlite also. So let us take this particular point 0.8 composition. So at point 0.8 composition, if you see, obviously you'll have single phase austenite with 0.8% of carbon anywhere that you take, and it happens to be so until it reaches this point, which is like a pure metal beginning and ending of uh, allotropic changes and eutectoid reaction. So if we take anywhere below that, it will directly convert, that is a pure eutectoid reaction, where directly it converts austenite to ferrite plus cementite. And this will how it represented, it will have alternate layers of ferrite and cementite. So if you see closely, it will have first austenite with the 0.8 percentage of carbon, so you don't have to remove anything in order to take part in the tetroid reaction. So what it will happen? So first austenite will form, will try to change its structure. So it will start by forming a plate-like structure. That is a cementite plate, and then either sides it will have a ferrite structure. Then again cementite plate, and then ferrite, cementite, ferrite. So like that, you have alternate layers of ferrite, cementite. It's basically a laminar structure, which is a fingerprint like structure, which is that represents a perlite reaction. So that's why you can see each grain is hatched, and it is orientation will differ from one grain to the other grain. So that is the perlite formation. Now let us move on and try to again observe another composition, which is at in the hyper eutectoid one. Let's take 1% of carbon. So at 1% of carbon, so it is in the hyper eutectoid side. So in that, if you take this zone again, it falls into a single phase austenite with 1% of carbon in all the grains dissolved. So this 1% of carbon, when you consider, it has so it has excess of carbon. Now, what does this line, upper critical temperature line on the hyperdeutectoid side of the steel, right? So now that already the beginning and ending of eutectoid temperature line is this one. That is allotropic change beginning and ending is indicated by this line A3 comma 1. Now, what does this line indicate? So this is something very interesting. So what happens here is this line indicates a saturation limit, like how we have certain amount of salt dissolved in water, and beyond a particular absorption or dissolving the salt, if you at all you want to have further more, you can heat it and then you can make it super saturated and then dissolve it. So it happens in very similar case in the solid solution in this particular case. That means this line above which the temperature will be high, so there it is super saturated, and this line indicates a saturation limit, so above which the carbon uh, is in excess, and below that you have a saturation carbon. So above there is unsaturated carbon, below you have a saturated carbon, so that line indicates a saturation limit. So if you see, it happens to be 1% of carbon until it reaches this line, where below that there will be a saturated carbon. That means whatever is excess more than zero point 0.8 will come out as a carbon, and it will transform as a precipitate, and it will try to form a cementite structure around the austenite. So wherever it is excess, it grows and then it forms this cementite structure. So you can see this darker portion, that is cementite around the austenite wherever there is excess. Now you tell me, for formation of cementite, how much carbon is needed? Yes, 6.67% of carbon is required. So austenite will lose point like 1% of carbon is there here, and how much is excess? 0.2, right? So that 0.2 will come out and form austenite, and sorry, cementite. So this cementite needs 6.6, so it grabs from the neighboring, and it will form the cementite around the austenites, and that's how it grows. And below this line, the austenite will only hold 0.8 percentage in order to take part in the eutectoid reaction, that is alternate layers of ferrite and cementite. But what is already formed will remain as cementite. So you can see here also what is already formed, that ferrite which has formed, that alpha which has formed will remain ferrite even here. The cementite which has already formed will remain cementite even below. But austenite, even here and here, it will try to maintain 0.8 configuration so that it can take part in the eutectoid reaction, forming alternate layers of ferrite and cementite. So that's what will happen even here. So ultimately, we have less than eutectoid reaction, pro-eutectoid ferrite plus ferrite. Why pro-eutectoid? Because it has formed already before the eutectoid reaction. So we continue to maintain the same thing. So we call that as a pro-eutectoid ferrite plus perlite. And here, obviously, you have only perlite, 100% pure perlite. And more than eutectoid reaction, you have, yes, pro-eutectoid cementite plus perlite. Okay. So feel free to go back for previous sessions where we discussed in depth about eutectoid reaction, iron carbide phase diagram, liver rule, and you can also pause and ask me for any clarification that is needed. Do subscribe and let me help you to learn this important iron carbide phase diagram. So thank you for watching. Have a nice day.